Process capability, monitoring techniques, gauge block sets. Individual gauge blocks may be purchased up to 20 inches in size. Naturally, the length tolerance of the gauge block increases as the size increases. Typical gauge block sets vary from 8 to 81 pieces based upon the needed application. The contents of a typical 81-piece set are 10,000th blocks, 9, 0.1001, 0.1002 up to 0.1009. 1,000th blocks, 49, 0.101, 0.102 up to 0.149. 50,000th blocks, 19, 0.050, 0.1 up to 0.950. 1-inch blocks, 4, 1.000, 2.000, 3.000, and 4.000. For the purpose of stack protection, some gauge manufacturers provide wear blocks that are either 0.050 inches or 0.1 inches in thickness. Calipers are used to measure length. The length can be an inside dimension, outside dimension, height, or depth. Some calipers are used for only one of these lengths, while other calipers can be used to measure all 4 types of lengths. Calipers are generally one of 4 types: spring calipers, dial calipers, vernier calipers, or digital calipers. Spring calipers. Spring calipers are transfer tools that perform a rough measurement of wide, awkward, or difficult-to-reach part locations. These tools usually provide a measurement accuracy of approximately 1/16 of an inch. Although these calipers are referred to as spring calipers, there are different varieties: spring joint, firm joint, lock joint, etc., which describe the type of mechanical joint that connects the 2 sides of the unit. A spring caliper measurement is typically transferred to a steel rule by holding the rule vertically on a flat surface. The caliper ends are placed against the rule for the final readings. See the figure. Vernier calipers. Vernier calipers use a vernier scale to indicate the measurement of length. Length, depth, and height are variations of the length measurement capability they provide. Resolution of vernier calipers is often 0.001 of an inch. Although vernier calipers are still available, they have been replaced with dial or digital calipers in many applications. Vernier calipers and dial calipers. The vernier scale. Vernier scales are used on a variety of measuring instruments such as height gauges, depth gauges, inside or outside vernier calipers, and gear tooth verniers. Except for the digital varieties, readings are made between a vernier plate and beam scales. By design, some of these scales are vertical and some are horizontal. Shown below is an illustrative example of how a reading is made. Dial calipers. Dial calipers function in the same way as a vernier caliper. However, the measurement is indicated by a combination of a scale reading to the nearest 0.1 of an inch and a dial indicating the resolution to 0.001 of an inch. The dial hand typically makes 1 revolution for each 0.1 of an inch of travel of the caliper jaws. Errors in reading the dial calipers often include misreading the scale by 0.1 of an inch or using the calipers in applications which require an accuracy of 0.001 of an inch, which is not realistic for this type of caliper. Digital calipers and optical comparators. Digital calipers. Digital calipers use a digital display instead of the dial and scale found in dial calipers. Most digital calipers have the ability to be read in either inches or millimeters, and the 0 point can be set at any point along the travel. Display resolutions of 0.0005 of an inch are common. Errors in reading the digital display are greatly minimized. However, like the dial calipers, digital calipers are often used in applications which require a different device to attain the required accuracy. For example, some digital calipers have data interface capabilities to send measurement data directly into a computer program. Digital caliper improvements have made them more reliable for use in machine shop conditions, including locations where cutting oil and metal chips come in contact with the calipers. Optical comparators. A comparator is a device for comparing a part to a form that represents the desired part contour or dimension. The relationship of the form with the part indicates acceptability. A beam of light is directed upon the part to be inspected, and the resulting shadow is magnified by a lens system and projected upon a viewing screen by a mirror. The enlarged shadow image can then be inspected and measured easily and quickly by comparing it with a master chart or outline on the viewing screen. To pass inspection, the shadow outline of the object must fall within the predetermined tolerance limits. Surface plates and micrometer surface plates. To make a precise dimensional measurement, there must be a reference plane or starting point. The ideal plane for dimensional measurement should be perfectly flat. Since a perfectly flat reference plane does not exist, a compromise in the form of a surface plate is commonly used. Surface plates are customarily used with accessories like a toolmaker's flat, angles, parallels, V-blocks, and cylindrical gauge block stacks. Dimensional measurements are taken from the plate up. Since the plate is the reference surface, surface plates must possess the following important characteristics: sufficient strength and rigidity to support the test piece, sufficient and known accuracy for the measurements required. Micrometers. Micrometers, or mics, are commonly used handheld measuring devices. Micrometers may be purchased with frame sizes from 0.5 inches to 48 inches. Normally, the spindle gap and design permits a 1-inch reading span. Thus, a 2-inch micrometer would allow readings from 1 inches to 2 inches. Most common mics have an accuracy of 0.001 of an inch. With the addition of a vernier scale, an accuracy of 0.001 of an inch can be obtained. Improvements in micrometers have led to supermicrometers, which, with laser attachments and when used in temperature and humidity-controlled rooms, are able to make linear measurements to 1/millionth of an inch. Micrometers consist of a basic C-frame with the part measurement occurring between a fixed anvil and a movable spindle. Measurement readings on a traditional micrometer are made at the barrel and thimble interface. Micrometers may make inside, outside, depth, or thread measurements based upon the customization desired. The two primary scales for reading a micrometer are the sleeve scale and the thimble scale. Most micrometers have a 1-inch throat. All conventional micrometers have 40 markings on the barrel, consisting of 0.025 inches each. The 0.100 inch, 0.200 inch, 0.300 inch, etc. markings are highlighted. The thimble is graduated into 25 markings of 0.001 inches each. Thus, one full revolution of the thimble represents 0.025 inches. Ring gauges and plug gauges. Ring gauges. Ring gauges are used to check external cylindrical dimensions and may also be used to check tapered, straight, or threaded dimensions. A pair of rings with hardened bushings are generally used. One bushing has a hole of the minimum tolerance, and the other has a hole of the maximum tolerance. Frequently, a pair of ring gauges are inserted in a single steel plate for convenience and act as go or no-go gauges. Ring gauges have the disadvantage of accepting out-of-round work and taper if the largest diameter is within tolerance. A thread ring gauge is used to check male threads. The go ring must enter onto the full length of the threads, and the no-go must not exceed 3 full turns onto the thread to be acceptable. The no-go thread ring will be identified by a groove cut into the outside diameter. Plug gauges. Plug gauges are generally go or no-go gauges and are used to check internal dimensions. The average plug gauge is a hardened and precision ground cylinder about 1 inch long. The go or no-go set is usually held in a hexagonal holder with the go plug on one end and the no-go plug on the other end. To make it more readily distinguishable, the no-go plug is generally made shorter. The thread plug gauge is designed exactly as the plug gauge, but instead of a smooth cylinder at each end, the ends are threaded. One end is the go member and the other end is the no-go member. If the go member enters the female threads the required length, and the no-go does not enter more than 3 complete revolutions, the threads are deemed acceptable. Dial indicators. Dial indicators are mechanical instruments for measuring distance variations. Most dial indicators amplify a contact point reading by use of an internal gear train mechanism. The vertical or horizontal displacement of a spindle with a removable contact tip is transferred to a dial face. The measurement is identified via the use of an indicating hand. Commonly available indicators have discriminations, that is, smallest graduations, from 0.00002 inches to 0.001 inches wide, with a wide assortment of measuring ranges. The proper dial must be selected for the length measurement and required discrimination. Pneumatic gauges and interferometry. Pneumatic gauges. There are 2 general types of pneumatic amplification gauges in use. One type is actuated by varying air pressure, and the other by varying air velocity at constant pressure. Depending upon the amplification and the scale, measurements can be read to millionths of an inch. In the pressure-type gauge, filtered compressed air divides and flows into opposite sections of a differential pressure meter. Any change in pressure caused by the variation in the sizes of the workpieces being measured is detected by the differential pressure meter. In the flow type of air gauge, the velocity of air varies directly with the clearance between the gauging head and the surface being measured. Interferometry. The greatest possible accuracy and precision are achieved by using light waves as a basis for measurement. A measurement is accomplished by the interaction of light waves that are 180 degrees out of phase. This phenomenon is known as interference. Interference occurs when two or more beams of monochromatic light of the same wavelength are reunited after traveling paths of different lengths. When the light waves pass from a glass medium to an air medium above the surface of an object, a 180-degree phase change takes place. The reflected light from the surface of the test object interferes with the light waves of incidence and cancels them out. Irregularities are evidenced by alternate dark and light bands. Laser-designed gauging and CMM. Laser-designed gauging. The use of lasers has been prevalent when the intent of inspection is a very accurate non-contact measurement. The laser beam is transmitted from one side of the gauge to a receiver on the opposite side of the gauge. Measurement takes place when the beam is broken by an object, and the receiver denotes the dimension of the interference to the laser beam. The laser has many uses in gauging. Automated inspection, fixed gauging, and laser micrometers are just a few examples of the many uses of the laser. Coordinate measuring machines, CMM. Coordinate measuring machines are used to verify workpiece dimensions using computer-controlled measurements which are taken on three mutually perpendicular axes. Workpieces are placed on a surface plate and a probe is maneuvered to various contact points to send an electronic signal back to the computer that is recording the measurements. CMMs can be driven by the computer to measure complex workpieces and perform automated inspection of complex shapes. Non-destructive testing, NDT, and evaluation, NDE. Non-destructive testing, NDT, and non-destructive evaluation, NDE techniques evaluate material properties without impairing the future usefulness of the items being tested. Today, there is a large range of NDT methods available, including ultrasonic, radiography, fluoroscopy, microwave, magnetic particle, liquid penetrant, eddy current, and holography. The advantages of NDT techniques include the use of automation, 100% product testing, and the guarantee of internal soundness. However, some NDT results, like X-ray films or ultrasonic echo wave inspection, are open to interpretation and demand considerable skill on the part of the examiner. Visual inspection. One of the most frequent inspection operations is the visual examination of products, parts, and materials. The color, texture, and appearance of a product gives valuable information if inspected by an alert observer. Lighting and inspector comfort are important factors in visual inspection. In this examination, the human eye is frequently aided by magnifying lenses or other instrumentation. This technique is sometimes called scanning inspection.